Hey everybody. Today we're talking about r squared, also known as the coefficient of determination. This is a number between 0 and 1 that measures the spread of observations about a regression model, or sometimes other statistical model. It represents the fraction of the variance in the response variable, the y variable, that can be attributed to changes in the explanatory variable, or x value. And this can also be applied when we have more than one explanatory variable. For linear models, r squared is always between 0 and 1. Larger values of r squared indicate that the data is more tightly packed about the regression line. So here I'm showing you three linear models. All those lines have exactly the same slope. On the left we have an r squared value of 0.2, in the middle 0.5, and on the right 0.8. A bit more precisely, r squared is defined in the variance of the fitted y values. So you take all your x values in your data set, you plug them into the regression equation to get the y values, you take the variance of that, divided by the variance of the observed y values. So that's literally just the variance of the y sub I, the observations of the y values in your data set. Using some math, you can show that that's equal to 1 minus the variance of the residuals divided by the variance of the observed y values. A relationship that often gets summarized, r squared equals 1 minus RSS over TSS. Residual sum of squares over total sum of squares. Important fact, in a least squared regression model with a single explanatory variable, the coefficient of determination r squared is the square of the coefficient of correlation. And that's to say that r squared is r squared. So in a sense, this is explaining the notation. I'm including the formula here for the coefficient of correlation, but of course this isn't something you should ever just plug into. You should compute that using technology. If you have a linear model with multiple explanatory variables and still just one response variable, then r squared is equal to the square of the correlation between the observed values and the fitted y values. You have to be really careful when working with r squared because it's very easy to misinterpret, and it gets misinterpreted all the time. Remember that r squared is a measure of variability, or spread about the regression line, much like coefficient of correlation is. On its own, it does not tell you how good a model is, or how good a fit the model provides to the data. Because by definition, r squared is naturally lower for data sets that have a lot of intrinsic variability. A couple of examples to illustrate that. Here's one showing you that models near r with r squared near 1 aren't necessarily good models. Here we have a data set that does not have a lot of variability. If you know the x value, it's pretty easy to predict the y value with a fairly high degree of certainty. But obviously the line that I've drawn over this is not a good fit. But just because the data doesn't have a lot of variability in it, if you compute the r squared value here, you get 0.93, which is very high. On the other hand, models with low r squared aren't necessarily bad, as this scatter plot illustrates. Here we have an r squared value of only 0.13, which seems pretty low, but this regression line drawn here is actually the best possible fit to this data. In order to get a higher r squared, we would have to overfit this data, making a zigzag that takes into account the natural variability in this data set as if it were an actual signal to be detected. Overfitting is not a desirable characteristic in your models. For these reasons and others, considering r squared in isolation when assessing a model is not a good approach. There are lots of tools for assessing linear models, and you should definitely take others into account and often give them higher primacy in your considerations. A big one to take into account is residual standard error, which represents the standard deviation of the residuals. Like r squared, RSE measures the variation in the data from the predicted values from the regression line. Unlike r squared, RSE does it on the same scale as the observations themselves, not as sort of a fraction of variance explained. And for that reason, it's a lot easier to interpret than the coefficient of determination r squared. Another useful way for assessing a regression model is by looking at the significance level of the regression. And if you have just a single explanatory variable, so your model has the form beta naught plus beta 1x, you can test the null hypothesis that the slope term is 0 just with a test statistic. There you're considering whether the slope of that regression line is truly 0 or not in the larger population from which your sample is taken. In other words, if there is a linear relationship between those two variables. In higher dimensions, you can use an F statistic to test whether there's a linear relationship as a whole between your explanatory variables and your response variables.